Thank you very much, Rick. And thank you to the organizers for inviting me here to give a talk. And first time at IPAM, it's very seamless and very nicely organized workshop. I'm really excited to present this material to uh, a, a group who does dimer models and probabilistic combinatorics. I've been always talking about this to knot theorists and hyperbolic three-manifold people, and I had to always put many slides about dimer model. So now I can completely skip that. So the theme is on the torus, we can connect various things. One is knot theory and hyperbolic geometry, but also number theory, which comes in terms of Mahler measure and computing Mahler measures, and dimer models, or combinatorics or spanning trees. So I'll start with some motivation, then a conjecture about finite planar graphs, how that conjecture goes into a conjecture about planar lattice graphs. We have some infinite families, and then coming back to the applications to the finite case. So the first motivation is the spanning tree order dimer entropy. This formula of temporally of the spanning tree entropy of the square lattice. And we get this, this formula comes into this Catalan's constant, but then geometers notice that the Catalan's constant, 4 times the Catalan's constant is the volume of the regular ideal octahedron. So all of the angles are pi by 2 and all the vertices are at infinity of the boundary of the hyperbolic free space. The second motivation comes from computing Mahler measure. So Mahler measure is an average of a polynomial is an average over the torus of log of the polynomial with dz by z. And for one variable, it is counting the roots outside the unit circle. For two variables, if you do that, the evaluations come up often in terms of the dilogarithm. And dilogarithm values are related to hyperbolic volumes. So this was the motivation for studying this Mahler measures and volume. So this was started. So for example, here is the volume of the figure 8 knot, which is the first sort of hyperbolic knot, and it's 2v tet. This is 2 times the volume of the regular ideal tetrahedron. And there is, starting with Smith, who computed the Mahler measure, I think probably the first Mahler measure for two variable polynomial 1 plus x plus y, and related it to special values of the L function. And that started off a whole computing Mahler measures for number theorists. And Boyd around 2000 was computing Mahler measure of A polynomials, which is a two variable polynomial invariant of knots and hyperbolic three manifolds coming out of representation theory. And he was noticing that these Mahler measures are actually related to the volume. And around the same time, and also in the same place, both Rick and David were both at UBC at that time. And Kenyon was computing, Rick was computing dimer entropies, and he would put a formula about exactly this volume of figure 8 volume of the Borromean rings or Whitehead rings as dimer entropies. So there is a whole number theory behind computing Mahler measures because of the relation to the L functions. But we were interested in there's the A polynomial part also, and that's how we got started seeing a talk by Rick at Columbia about 20 years ago to really see what is going on and how the figure 8 knot is appearing or the Whitehead link is appearing. So
I'm sorry. All these are different things, but it's the same volume. I don't understand.
Yes, it's the same number.
Same number.
It's the same number. It's the volume of the figure 8. I've just arranged it so that you get volume of the figure 8 on the left hand side and arrange the constants like that. Yes. But after the scaling, it's the same number which appears like this.
Just different representations of it.
Yes. And it's related to, for example, Boyd's formula is related to the fact that the figure 8 knot complement is arithmetic and the A polynomial variety has some arithmetic properties, and there's an and for example, Rick's formula is about dimer entropy. The volume is not the key point. The volume, the number V tet is what appears. So the first conjecture we have is for a finite connected planar graph, the number of spanning trees, and this has been studied forever, and I'm not going to even go into the literature because I don't know enough of it. You are probably more expert at the counting of spanning trees literature. But what we gave is a lower and upper bound in terms of geometry. So I'm just going to explain you what the terms are here. Tau of gamma is the number of spanning trees. E gamma is the number of edges, or the set of edges. B oct we just saw, it is the volume of the regular ideal octahedron, that is the upper bound. And volume of gamma is the new quantity here, which is what we defined, which will define as the hyperbolic volume of the graph. So which I'm just going to explain now. Just take a little detour about knots, graphs, and geometry. So what is the detour in knots and graphs? If you have a planar graph, you can, using the medial construction, construct an alternating link. Now, typically there is a sign involved there, but if you insist on everything being alternating, all of the signs are the same and you can ignore it up to mirror images. And similarly, if you have a alternating link diagram, you can checkerboard color it and then take the checkerboard graph and get a planar graph from it. Now these graphs are not necessarily simple, they have multiple edges, they can also have loops depending what your knot looks like, knot or link diagram looks like. Now the link determinant of K is an important invariant. It was one of the first invariants defined by Seifert as the determinant of the symmetric Seifert matrix, which was not a minimize over all diagrams kind of invariant. And it has been reinterpreted again and again, and every time you get a new sort of theory, you try to see where the determinant fits in. In particular, for an alternating link with the Tate graph, the determinant is the number of spanning trees of the Tate graph. So we just get, here is a figure 8, here is the Tate graph, and you can count its 5 spanning trees. So so there is a determinant. There's a knot invariant coming from graph theory here.
Is this some specialization of like Alexander polynomial?
It is specialization of Alexander polynomial, specialization of the Jones polynomial, yeah. And if you are non-alternating, you can get a weighted sum of the spanning trees. Yes?
Two questions about this slide. What is K? The matrix is K?
What is K? K is the link, alternating link.
Determinant of K?
Yeah, determinant of K I did not define. I'm kind of defining for alternating as the number of spanning trees. But it is defined as a determinant of a symmetrized Seifert matrix for the knot. Yeah.
And the second question is about the edge weights, +4 +1.
Yeah, the edge weights, yeah, there is a ordering on the vertices, and the plus is a sign which, if it's alternating, all the signs are the same and we can ignore it. The numbering is the ordering. Yeah. Yes.
It's defined for non-alternating knots too, right?
It is defined for non-alternating knots as a weighted sum of spanning trees, because you get edge weights coming from the signs. So you get an alternating sum. It's a sign sum.
Weighted sum of spanning trees.
Yes.
But they're, all the weights are 1. All the weights are plus or minus 1.
Plus or minus 1, yes. And now the geometry of knots. So link is hyperbolic if its complement has a finite volume hyperbolic, is a finite volume hyperbolic 3 manifold, which means that the fundamental group acts on the hyperbolic 3 space via properly discontinuously and via isometries. So for hyperbolic alternating links, we have this theorem of Manasco, which lets us skip all the geometric computation or representation, finding representations or constructing geometric gluings. Manasco showed that if K is a connected prime alternating link diagram, if it is hyperbolic unless it is this sort of 2K torus diagrams. And these are, if you take the Tate graphs of it, these are all the wheel graphs. So if you have a planar graph, if it's a connected planar graph, maybe two connected, so because it's prime, so if it is not the wheel graph, then you are hyperbolic. And so we can, so the knot invariant from geometry which comes, one of the most important invariants is the volume of the knot, which is the volume of the hyperbolic manifold, which is the knot complement. And it's a geometric invariant, but it is also a topological invariant because hyperbolic structures are rigid. So you get this geometric invariance or topological invariance by Mostow-Prasad rigidity. So for example, if you go back to our figure 8, it can be decomposed. How do you find the volumes? You decompose them into geometric pieces and then compute the volumes of the individual pieces. So for example, the figure 8 knot complement can be decomposed into geometrically into two regular hyperbolic ideal tetrahedra, hence that's the volume 2V tet. And the Borromean rings here can be decomposed into two regular hyperbolic ideal octahedra. So the volume is 2V oct. Any questions? Yes.
There's always some integer multiple of these two simple numbers, or I guess not.
That's what it seems like because we just showed those examples. No, not at all. No, they can be pretty much whatever the spectrum of the hyperbolic volumes of tetrahedra are. Yeah. So now we come back to the conjecture, and the lower bound now is the volume of the knot where K is the alternating link whose state graph is gamma. So now we have a geometric quantity which gives a lower bound for the spanning trees. So let me just say a little bit about this conjecture, about where it came from. The upper bound is conjectured by Rick in 1996. It's a comment in his 1994 paper on tilings of a rectangle by squares. And so, but the V oct doesn't appear, the Catalan's constant appears. And then if you scale in properly and take the proper multiples, you get V oct right there. The lower bound is a conjecture from knot theory with Ilya Kofman and Jessica Purcell. It's called the wall-det conjecture. So we saw the two invariants of alternating link. One is the knot determinant and one is the hyperbolic volume. How are they related? Well, there is an inequality there. So you can see that this if gamma is a Tate graph, then 2 pi log number of spanning trees is the 2 pi log det, and the lower bound is the volume. So there is a volume determinant conjecture there, and this has been verified by us for all the census knots, which is about 1 million knots, up to 16 crossings, maybe even up to 17 crossings. Yes?
You know that the volume is always less than the upper bound?
Yes, that it is. I'm going to just explain why the lower bound is always smaller than the upper bound. Great question. The non-trivial fact here is the 2 pi is sharp for this conjecture. What does that mean? If you take any alpha which is less than 2 pi, then we can find some graphs whose volume beats alpha times log of the spanning trees. And the same thing, if you take any alpha greater than 2 pi, then we can find some knots whose the number of edges times V oct is less than the thing. So this 2 pi is actually sharp. So now we can go to the toroidal conjecture. Second conjecture. Any questions so far? Okay. So first we want to mimic all of this. So we first define the volume of a toroidal graph. So you have a toroidal graph, and then we take a link whose state graph is this. I'm talking about toroidal graph, but you can think of this as a planar lattice graph, which is a biperiodic graph. And we can take the Tate graph and we can get the corresponding link on a link diagram on the torus, and we can think of this as a alternating link in the thickened torus. So you have an alternating link in the thickened torus right here. So we have these are infinite objects, There's a link, and then the L is the link in the thickened torus, and G is the graph on the torus, like so. And now we can define the volume of G here as the volume of the link complement, but not in S3, but in the thickened torus. And then we can define for the upper bound, we can define the volume of the script G as this volume of, no, this is still the lower bound. So this is the volume in the fundamental domain per vertex. So this is, you can think of this as the volume density, it is a volume per vertex.
Sorry, but then, like, since you are now living in the thickened torus, maybe you don't have most of rigidity, or maybe you don't have, like, the notion of hyperbolicity is different.
Great question. Couldn't have planted it better. Exactly. I'm going to tell you about the geometry. So the geometry of biperiodic alternating links. Fortunately, we still have Mostow rigidity. So why is that? So here is an example of what is the square weave. And so if you take a biperiodic link, we get a link in the thickened torus. So if you imagine this link as on the projection plane R2, and we are, if it's quotiented, you get something in the thickened torus, the actual link. Now the key observation is that the thickened torus is actually S3 minus the Hopf link. This is the Hopf link coming the course of the Hopf fibration. So, and S3 minus the Hopf link is actually a thickened torus. And so what we get is this link here is actually a link complement. If you combine it with the Hopf link, it's a link complement in S3. And so you actually have the everything what Mostow rigidity needs, which is basically having torus cusp, this torus boundary components. So everything fits that. So you actually have finite volume hyperbolic structures on this. And so here is an example for the square weave. If you compute the hyperbolic structure, you can actually draw this link, give a link diagram in the plane, and there is your Hopf link, and now we can plug it into various softwares like Snappy and get the hyperbolic volume. So in this particular case, we actually get 4 times V oct in this particular, for the square weave.
So it will be an invariant not of the original link, but of a link together with the Hopf link.
It is the invariant of the original link. Because there are, if it's alternating, there are all kinds of diagrammatic rigidity on the torus. But the link is in the thickened torus, so this is the manifold, and that has a geometric structure, and there is Mostow-Prasad rigidity on this. So the invariant is of the link in the thickened torus. Yes.
If you apply a Dane twist to the torus, does that change could that possibly change the volume?
It will.
If you're changing how the link is intersecting the Hopf link.
Yes, that will change the volume. Yes. And now we can also compute it explicitly. Here is an example of this particular link, the square weave, and this is a circle pattern which is showing you 4 octahedra. So here are the circles, and the straight lines are also. You are seeing from the point at infinity, you are looking into the hyperbolic upper half space model, and the circles are representing hemispheres, and these lines are representing vertical half planes. So all of this is cutting out of an infinite biperiodic hyperbolic polyhedra. And now if you take the fundamental domains, these triangles are representing some phase gluings of this finite polyhedra. And this is explicitly giving you what the structure is, not just the number for the volume, but actual hyperbolic structure. So now we come to the conjecture. So you start with a planar lattice graph preserved by some lattice lambda, and now we take the exhaustions, a nested sequence of the finite planar graphs, and we define the spanning tree entropy as the asymptotic growth rate of the spanning trees per vertex. And this is related to the dimer entropy as this is equal to the dimer entropy per vertex. So if you think of the dimer of the overlaid bipartite graph for G, if you take G and take the dual of it and overlay it, you know all this, sorry. So the conjecture now is upper and lower bounds for the spanning tree entropy. So now we have the volume here, which is exactly defined as the volume of this graph, which is the volume of the link in the thickened torus per vertex. So this is some volume density. And here it is the number of edges times V oct, again per vertex. And so we have this conjecture for upper and lower bounds for the spanning tree entropy of this planar lattice graph. So examples. So let's take the square weave here. This is the Tate graph for the square weave. And you take the fundamental domain where there is one vertex. You compute this as we saw in the first motivational slide. This is what the computation, and this is exactly gives you an equality. For this case, the upper bound is also equal. So the whole inequality falls into equality everywhere. And there is the honeycomb lattice, and we have seen that many times during this conference also, and we get the 5 V tet. This V tet is exactly the number which comes up, and now we can see that it is actually the volume of a link which is associated to this, a biperiodic link or a link on a torus rather than the figure 8 knot or the Borromean rings. And again, you can do this, there is just duality here except that one has to keep track of the vertices. So for these sort of regular lattice graphs, you actually get equality. So it's, but it is not an equality. I'll show you more examples, but before that, I just want to go into where the upper bound is coming from. So there is a construction where you take a link diagram and you add a octahedra at every crossing. And this octahedra, you get an octahedral decomposition. And this is how a program, the most used program for computing hyperbolic structures, SNAPI, this is how it triangulates link diagrams. If you draw in a link diagram, it puts in an octahedra and then takes the decomposition like that. Now what happens is that once you get an octahedral decomposition, this is as many as crossings, octahedra, and any octahedra, the volume is going to be less than the regular ideal octahedra, which is the maximum volume. So the volume of the link complement is strictly less than the crossing number times the V oct. Now, in order to prove the conjecture, if you just go back here, or prove for some cases, this number seems a little difficult to relate. So there is a number in between here, which is what we come up with. So what we do is we take this octahedral decomposition and reconfigure it. So how do we reconfigure the octahedra? We divide this octahedra, just stellate it into 4 tetrahedra meeting at one edge. And then you take a tetrahedra which is there at every crossing, and now you look around at a face. And now you collect this tetrahedra at every crossing, which is coming from this octahedra here, but one tetrahedra only when you look at it from the face, and you combine them together. And when you combine them together, you actually get a bipyramid on this face. So you actually get a bipyramid on every face, and the volume of a bipyramid is less than the volume of a regular ideal bipyramid. And so we get a bound which is called the bipyramid volume. So here is the regular ideal bipyramid, and we can compute the volume simply by using Lobachevsky functions and subdividing it into tetrahedra. And so for example, the ideal octahedron which we have been talking about is the 4 bipyramid. And Colin Adams here computed these volumes and actually showed the growth rate is 2 pi log of n by 2. So what we can do now is we can get a bipyramid volume of a link by just taking the order of the faces and taking the volume of the regular bipyramid. So just by definition and because of the decomposition, this volume of the link is actually bounded above by this bipyramid volume. The interesting part is in this conjecture, the bipyramid volume, oh sorry, this is the bipyramid volume of, did I go back? No. Yeah, I just wanted to mention the bipyramid volume of a graph. So now if you're taking a graph on a torus and a dual graph, we compute the bipyramid volume just as the bipyramids on the faces, but then we also need to do this for the dual graph because of the Tate graph only catches half the faces, the shaded faces. So we define the volume of a graph as the bipyramid volume of G and G star. So it's catching every face.
Abhijit,
Yes.
so here you have the medial graph of your original graph, which is each vertex has degree 4, and you somehow attach to each corner of this medial graph a tetrahedron, is that correct?
Yes, we are, if you go back here, there's a tetrahedron here and the tetrahedra combine to give you a bipyramid here.
And so then you are trying to combine these tetrahedra either around the face or around the
Yeah,
vertex.
there is a way to glue these bipyramids together, but that gives you the topology. But for the bound, we only need to know the order of the face because the order of the face gives you the volume of the regular bipyramid, and the regular bipyramid will give you an upper bound here. Yeah. So you do the same thing for the graph, and then you get, so the bipyramid volume of a lattice graph now is the bipyramid volume of G and the bipyramid volume of G star. So you're catching all the faces of the link per vertex. Now this, interestingly, goes below the dimer entropy, and most times. So if you are, this is a much more combinatorial quantity, and if you can show some inequality over here, then we can get this conjecture. So what happens is, for the regular lattices, of course, it is an equality. So what happens for other lattices? So here are some, so these are the lattices, and then we computed ZG by using the dimer entropy, compute the characteristic polynomial and numerically compute the Mahler measure. But we have a paper where we explicitly compute Mahler measures. There's a paper with Matilda Lalande where we compute using the number theory part, get actual volumes, exact numbers. So these are the upper bounds and these are the lower bounds. So it's very reasonable to conjecture that this is always greater than this part, which is what, yes?
And do you have conjectures of when you achieve the upper bound and when you achieve the lower bound?
The lower bound, they are achieved for 3. The question is there any G other than the regular lattices for which this is an equality? So we do not know, and we guess no. We don't get anything else where it's equal. So we first thought this is always true, this is greater than this number, but then we found an example for which it is not. So the conjecture 2 holds, but this bipyramid volume beats the entropy, spanning tree entropy. And this is the only graph we know, and we have no idea why it fails, because it is so many other graphs. I have no idea. It's not even that crazy or exotic. It is very simple. It's just something just goes wrong. It's very frustrating. So, however, using whenever this holds, no, not this one, sorry. Whenever this holds, we can actually prove the conjecture infinitely many cases. So the first is that if you replace every edge by parallel edges, then we can still prove the conjecture. And of course, the original graph satisfies the conjecture, then the new graph also satisfies this conjecture. We can also truncate a 3 regular lattice graph. So by truncating this, again we can continue this process, and this will also satisfy the conjecture. There is also a medial graph of the 3 regular lattice graph. So, so these are constructions. Why these particular constructions? We only do this because we found a paper by Teufel Wagner which computed the growth rate of the spanning tree entropy under these operations. And so we are not doing anything fancy here. We just show that the bipyramid volume actually also behaves exactly like this. And so under these moves. And so we get it for almost free. Okay, so going back, all right, so we have all of these graphs which satisfy this conjecture 2, and I said that we'll come back to the conjecture 1. So what is the, how to go back to conjecture 1? So this is something which we did for knot theory, and we are adapting everything for in this graph theory context. So we were trying to study what is the maximum volume per crossing for a knot. So there's the upper bound, which is the number of edges times V oct. So we wanted to see if that can be realized. So again, per crossing. And we know for the square weave, just explicit computations, we know that the volume per crossing here is V oct. So if we could have a sequence of knots or links which approach the square weave, so you take bigger and bigger parts, you close it up somehow in a controlled way, and we can show that the volume density converges, so volume per crossing actually converges, then we would have the upper bound. And so this is what the Follner convergence almost everywhere is. It is a nested sequence, but you are allowed to close it off in any way, except that you cannot add too many crossings. So the number of extra crossings you are adding to close off this link, they don't have too many crossings. So this is your Follner convergence. And so what we proved is that the volume density converges under this Follner convergence, so you actually get this upper bound for these infinitely many links. So now what happens is, so I'm going to, well, this is, you have a link, you get the bipartite graph, and then you have the dimer model, and you have the Mahler measure here, so we compute a dimer entropy. So we also proved that the determinant, the log of the determinant converges per crossing, converges to this dimer entropy. So as you go on increasing, not only does the volume density converge, the determinant density also converges here. So now you can see where this conjecture 2 is coming from, that there is a determinant density convergence and there's a volume density almost convergence. We only can prove the volume density convergence for only a couple of lattices. So now, if we know the conjecture 2, we can get infinitely many cases of conjecture 1. So you have a planar lattice that satisfies conjecture 2, and there is a strict inequality over here. And now if you take gamma n to be a sequence of connected planar graphs with bounded average degree that Follner converges to G almost everywhere, then because this determinant here converges over here, then in some and there is a bipyramid volume here, and we can show that the bipyramid volumes also converge. That's because this is a combinatorial quantity. So we have something over here which converges to this part. So now we can just use the fact that there is a converging sequence here to get that the volume is strictly less. So we get infinitely many cases of conjecture 1 from conjecture 2. So this is a case where you can get something for the biperiodic case, and now you can use some approximation to go to the finite case. And as I said, the proof here is that we use this bipyramid volume because that behaves well under this Follner convergence. We do not know if the volume, hyperbolic volume, behaves well except for a couple of cases. That is harder to prove. And of course, the determinant density convergence, which is this convergence over here. And the upper bound is just easy to. So here are a couple of examples. Oh, I have more time. So this is the rhombic trihexagonal link. We like this because after the square weave and the hexagonal lattice, where everything we got equality and were very optimistic, we computed this the various quantities for this link, and we were shocked to see that it's not equal. So we computed the volume of this, and you can see this is a combination of the regular tetrahedra, regular octahedra. So you would think everything comes like that, but that is not so. This is a very special link. This is what we call a semi-regular link because the faces are all regular polygons. And in fact, there are only, if you take the 4-valent, you only have 3 polygons which can occur, the squares, the hexagons, and the triangles. And now we can compute explicit geometry of this, and we can write down an expression for the volume of this in terms of how many triangles and squares are occurring. So in this case, the fundamental domain has 3 squares and 1 hexagon. 1 hexagon and 2 triangles, so that gives you 10 and 3. But then, so this is not a this computation is not an approximation; it's an exact computation. And then we have the dimer polynomial for this, the characteristic polynomial for this, and we can compute the Mahler measure of this. This is also an exact computation, and we see that they actually differ. This is bigger. So when we saw this, when you get lemons, you can make lemonade. So we saw, what can we do? So we realized we can use this to show infinitely many cases of the Wall-Det conjecture, because we knew this converged to the the determinant converges over here, and the volumes are, these are as big as the volumes can get. And so we can actually get infinitely many cases. So this is coming out of, so we got infinitely many cases of the Wall-Det conjecture. So this is technology from knot theory just reinterpreted for graphs. And here is another example, just to give you a sense of what the bipyramid volume looks like. You take some, we call it a typical biperiodic link, but probably not. A word typical to use in this audience is really bad. So apologies for that. You have octagons and pentagons and squares and triangles. So this is the combinatorial quantity which you can just compute. And it would have been great if this combinatorial quantity would be a lower bound for the dimer entropy. You would not have to do any sort of hyperbolic geometry and compute volumes. This would have been great, but it just doesn't work. There is this one example which really spoils the day. And so there the conjecture is. Since I have a few more minutes, I just want to discuss a slightly more combinatorial lower bound for the dimer entropy, in which holds in special cases. So what are the special cases it holds in? You look at the graph, the biperiodic graphs, script G and script G star, and we call them orthogonally dual lattice graphs if the inscribed circles in their faces form an orthogonal circle pattern. So this orthogonal circle pattern, what this gives you is, it gives you for the corresponding links, they are what is called right angled links, meaning that their complement can be expressed in terms of a right angled polyhedra. And so for a right angle polyhedra, the volume is easier to compute. So it is, once you know the local angles for right angle polyhedra, we can compute using the local angles. And we have proved with Ilya Kofman and Jessica Purcell that the right angle volume is a lower bound. So our statements are for not links, but if you take your graphs to be the Tate graphs of the links, then this can be reinterpreted for the graphs. So the right angle volume is a lower bound for the volume, which is again a lower bound for the bipyramid volume. And so the spanning tree entropy sits somewhere over here, and we can get this from local angle considerations. And so we can compute this, but we need this orthogonal dual lattice graph. So how common is this orthogonal dual lattice graphs? More common than regular lattices. So so how do we see the orthogonality? Maybe, let's see. Yeah, so for example, when we overlay it, we get these right angle kites everywhere. And so the right angle kites are the ones which are giving us the orthogonality, and then we can compute the volume, the right angle volume, by just evaluation of Lobachevsky functions at these kite angles. And so this is a local sort of computation which is easier than computing the actual hyperbolic volume, and gives you a lower bound. So for all of these lattice graphs shown, we have this inequality. So this is only for the lower bound. And here is the same example which doesn't work for this bipyramid volume thing. The right angle volume again it's very close. All of these numbers are very, very close. And it's not obvious if you draw the graph like this that it satisfies orthogonal duality, but if you draw it in the slightly different way, it actually does satisfy orthogonal duality. So these are some of the references, papers with Jessica and Ilya and Matilda, and this paper is still waiting to be posted. Thank you very much.